All right, let's get right into it. Today, we're going to unravel the story of a single molecule that has been both a hero and, well, a villain in the world of chemistry: benzene. Seriously, its journey from a common household product to a known danger is a chemical detective story, and we're about to crack the case. You heard that right. It's kind of hard to believe, isn't it? But it's true. Way back in the 19th and early 20th centuries, benzene was a key ingredient in aftershave. Not only that, it was used to decaffeinate coffee and even as an additive in gasoline. I mean, this stuff was everywhere. So let's just trace this wild ride. The brilliant Michael Faraday first isolated it way back in 1825, and that discovery kicked off decades of widespread use. But then, by the 1950s, you start to see the tide turn as it got replaced in gasoline. And now, well, our understanding has done a complete 180. And there it is. That's the twist in the story. As our ability to test chemicals got better and better, the truth came out. Benzene was officially identified as a carcinogen. So that begs a huge question. What is it about this specific molecule that makes it so useful, but also so dangerous? The answer, it turns out, is hidden in its very structure. And that brings us right to the heart of the mystery: the structure of benzene itself. For decades, this thing was a total puzzle that stumped chemists because it just didn't seem to follow the rules that every other chemical played by. First, a little bit of terminology. Benzene is the simplest example of something we call an aromatic hydrocarbon. Okay, let's break that down. Hydrocarbon, you got it, made of hydrogen and carbon. Cyclic, it's a ring. And unsaturated means it has double bonds. But the key phrase here, the one that causes all the trouble, is chemically stable. And this is the question that probably kept chemists up at night. See, molecules with double bonds are normally really reactive. They're just itching to break those extra bonds and connect with other atoms. But benzene? Nope. It was just strangely, stubbornly stable. So why? This is where the mystery gets even deeper. Logically, if you have alternating single and double bonds, you'd expect them to be different lengths, right? Some short, some long. But when scientists actually measured them, they found something incredible. All 6 of the bonds were exactly the same length. The theory just did not match reality. And the solution was a truly revolutionary idea. It turns out the electrons aren't locked into 3 specific double bonds. Instead, they're delocalized. Think of it like an electron racetrack, where those 6 electrons are just constantly zipping around the entire ring, shared equally by all 6 carbon atoms. And all that sharing creates an unbelievably stable structure. This new understanding completely changed how we draw the molecule. The first guess was just a simple hexagon with alternating double bonds. Then, for a while, chemists drew it as 2 different structures that were constantly flipping back and forth. But today, the most accurate way to show that awesome electron sharing is with a circle right inside the hexagon. That circle represents that super stable, shared racetrack of electrons. Okay, so now that we get the structure, let's learn the language. How do we actually talk about and name these molecules? It might seem complicated, but it's really like cracking a code. And once you see the pattern, it's surprisingly straightforward. There are really just 2 main rules you got to remember. First, if the benzene ring is the star of the show, the main part of the molecule, we name everything else as an attachment to benzene. But if the ring is just a little side piece on a much longer chain, we call it a phenyl group. Let's try that first rule out. In this molecule, the benzene ring is clearly the parent. So the game is to number the carbons to give the attachments the lowest numbers you can. Doing that puts an ethyl group at position 1 and 2 methyl groups at positions 2 and 4. You put it all together, and what do you get? 1-ethyl, 2,4-dimethylbenzene. See? It's just a system. Okay, now let's look at the other rule. Here, the main event isn't the ring at all. It's that long 6-carbon chain. That's a hexane. The benzene ring is just hanging off the 3rd carbon. So in this case, we call that ring a phenyl group, which makes the full name 3-phenylhexane. It's all about figuring out what the parent chain is. So we know benzene is stable, but what does that actually mean for how it behaves? This is where the story takes a really fascinating chemical twist. Its stability doesn't just make it strong. It makes it act in a way that just defies all expectations. So let's set the stage here. Normally, molecules with double bonds, like alkenes, that's ALKENES, They love to undergo what are called addition reactions. They basically just break a double bond to add new atoms right into their structure. That's their standard playbook. But benzene, with that incredibly stable ring of shared electrons, it just refuses to play by those rules. It will do pretty much anything to avoid breaking up that special, stable structure. And here it is, the big reveal. Look on the left, you've got cyclohexene, a pretty typical ring with one double bond. When it reacts with chlorine, that double bond breaks open and 2 chlorine atoms are added. But now look at benzene on the right. It doesn't break its ring structure, no way. Instead, it substitutes one of its hydrogen atoms for a chlorine atom. It just swaps one out instead of adding. So here's the bottom line. Even though benzene is technically unsaturated, it acts like a saturated molecule. That unique, super stable ring of electrons is so strong that benzene would rather kick off a hydrogen and replace it than dare to disrupt the ring itself. The puzzle is officially solved. And all of this brings us full circle. You see, understanding benzene's unique chemistry isn't just some random academic exercise. It's exactly what allowed scientists to finally understand its risks and, more importantly, to find safer ways to do the jobs that it once did. And the reasons for moving on from benzene are, well, crystal clear. Once it was identified as a carcinogen and linked to other serious health risks, the scientific and industrial world knew they had to find alternatives for, well, pretty much everything from solvents to dry cleaning. A perfect example of a replacement is toluene. Hey, using the rules we just learned, you could also call it methylbenzene, because it's just a benzene ring with a small methyl group attached. That one tiny little change is enough to make it a much safer solvent. It's just a fantastic example of how deep chemical knowledge leads to real-world safety improvements. And that leaves us with one final thought. The story of benzene, from aftershave ingredient to carcinogen to a solved chemical puzzle, it just goes to show how our understanding is always changing. It really makes you wonder, doesn't it? What common chemicals that we use every single day might be holding similar secrets that we just haven't uncovered yet?